Maybe I can try to extend my screen. Hi, hello everyone. Thank you for coming today. Today will be our final talk at Amii, and we are very grateful that Amii has providing us this space, and Corey and Scott has been helping us recording, and we'll be very grateful for that. And today we have Gautham and his topics on reward functions and some robotics tasks. And let's welcome.
Okay. So hi, I'm Gautham. I'm a PhD student with Rupam, and yeah, I'll be talking about reward functions and robotics. So I'm going to start with this question. So how to solve reinforcement learning tasks? So that's a question that's something we all care about. We think about this deeply. But this question presupposes that you already have access to a well-defined MDP. Right? So you have an MDP. If you solve this MDP, you're going to get an optimal policy. But I'm going to talk to you about a step that precedes that. I'm going to talk to you about how to specify a reinforcement learning task. So this means you don't have an MDP yet. You have an abstract problem you want to solve that's in your head, and you have to formulate this as an MDP. So imagine you're a reinforcement learning practitioner. You have a robot arm, and you want this robot arm to do a bunch of different tasks. So if you have reinforcement learning, you have this nice MDP formulation where you have this nice delineation between the agent and the environment. The agent can perceive the world through an observation. So in this case, let's say you have images, you have proprioception information, and the agent can influence the environment, and it can do so using joint torques. So when it takes an action, it's going to get a reward signal. This reward is a scalar reward, and I'm also assuming an episodic setting, which means you have a terminal state or a termination condition. So typically, this can be something like you have a goal state, and once the agent reaches the goal state, the episode is done. Or maybe you have a time limit. So you have a time limit of, say, 1,000 time steps, and the episode is done after that. So if you just look at this, if you want to solve a bunch of different tasks with the robot arm, maybe you can keep this observation and action space fixed. But based on the choice of the reward and the termination condition, I can tell the agent what task it is solving. So if I'm the task designer, my choice of the reward and the termination condition, that's going to define the task. So let's take an abstract problem. So let's take the reacher problem. So the reacher is this two-jointed robot arm. So the goal here is for this robot arm to swiftly reach the target sphere and remain there. So you see the fingertip here. So the goal is for this fingertip to go inside the target sphere and just stay there. And each episode, this target can be spawned anywhere in the arena. Right? So if I want to specify this problem as a reinforcement learning task, I'm going to start with an observation space. I'm going to think about the minimum information I need so that I can solve this task. So I'll consider the position of the fingertip, the velocity of the fingertip, and the Cartesian goal position, because each episode the goal changes, so I need to know, the agent needs to know where the goal is so that it can reach there. And the action space would be the joint torque applied. Now that we have the observation space and the action space defined, we can think about the reward and termination conditions here. And there are quite a few choices, because the abstract goal in itself, it's just to reach the target and stay there. But you can achieve this through a combination of different rewards and terminal conditions. So let's take a common reward signal. So this is a reward which is based on the OpenAI Gym Mujoko Reacher task. So let's look at this component first. So you have a measure of the Euclidean distance. So we are telling the agent, if you're close enough to the goal, you'll get a small penalty. If you're farther away from the goal, you'll get a large penalty. And then we're also telling the agent, if your action is large, you're going to get penalized for it. So you want to avoid any jerky movements, and we are emphasizing that the movement should be smooth. In addition, you have another reward, which is +1 whenever you're inside the target. So this is to incentivize the target to remain there. So for such a simple task, this might seem like a complicated reward function, but this is fairly common in robotics and any benchmark task you take. So this is also known as a dense reward formulation. I'm calling this a guiding reward because it goes beyond what a reward function is supposed to do. It guides the agent towards what it's supposed to do. So we have a fixed episode length of 1,000 time steps. And in this case, the episodes are truncated. You don't really have a terminal goal state. So when you have 1,000 time steps, the episode is considered done. So I've cited the OpenAI gym paper here, but it's also something that I have used, and I've done this with Rupam on a different paper before. So this is fairly common. We can simplify this reward function and make this sparse, and I'm calling this the contact reward formulation, because whenever the agent comes in contact with the target, you get a reward. So in this case, you just have a 0 or 1 reward. So if you're in contact with the target, you get a reward. If you're outside the target, you just get a 0. So this setting here, it's just a simplification of the guiding reward formulation, and this is the standard reward formulation you have in the DeepMind control suite. You can have another reward formulation here, which is just a -1 every time step until the episode is done. So for this agent, life is suffering. The episode should be done as soon as possible. You want the agent to be done with this episode as soon as possible. So the termination condition here is once the fingertip is inside the target, and it should also have near 0 velocity, that's when the episode is done. So for the previous formulations, we said nothing about a velocity constraint. All it has to do is it should be within the target. In this case, we want it to be inside the target, but it should also have a near 0 velocity. But when we formulate it this way, we don't have a fixed episode length anymore. We're going to have episodes of varying lengths. So this is very similar to the mountain car formulation, but I'm also going to add one more thing here, because I don't want the episodes to run infinitely long. So if the episode reaches a timeout of 1,000, we'll reset the arm, but the target is going to remain the same. So the arm goes to a different location, it incurs a penalty, and the episode goes on. So this way, it's like we avoid having infinite length episodes. So we have 3 different formulations now for the same idea. It's like we want the arm to reach a target and stay there. And you can formulate this in 3 different ways, and we don't know which formulation will actually be the best. Yeah. So that's still a timeout. So in this case, the episode is done. It's considered done. But in case of the minimum time formulation, the episode is not done. Yeah, once you reach the target, and you can just stay there, and you can still continue getting rewards. Any other questions? Yes. Right. Yes. So I'm going to I have a bunch of slides that are related to exactly what you're saying so far. And yeah, I'll elaborate on that, yes. Yeah. So if you get a 0, it's like, you don't have any information early on. So it'll be a lot of delayed information. So the learning would be. But I'll answer that as well in the upcoming slides. So I'm going to evaluate these 3 formulations using 3 metrics. Because the first one would be ease of specification, which is, as a task designer, how easy is it for me to specify this? So if I have the domain knowledge, maybe I can do something like the first formulation, where I have a bunch of different components, but that's going to be hard. And I want to evaluate this based on 2 other metrics, which is how fast is learning, and does it actually achieve the desired behavior? Yeah. So the behavior is just something abstract you have in your mind. You have this robot arm. It has to go from point A to point B, and you want this done as efficiently as possible. Right? So you go to point B, and you just stay there.
By efficiently, you mean as fast?
Yes, as fast as possible. If you do have jerky actions, it's like it won't be the most optimal policy because you're supposed to stay there. But yes, yeah. Yeah.
So I was going to say, jerky actions seem to be hard on your hardware once the hardware is stored. Is that part of the guiding reward formulation?
Yeah, that's the idea. So a lot of people in robotics, they worry about damaging the robot arm. And so they have an additional component like this so that you can dissuade the agent from doing anything risky. Yes, Patrick, yeah.
You were saying in your guiding word formulation that you're penalizing the jerkiness in motion. You're just penalizing the action entity, right? This isn't actually saying anything about any of the derivatives of the motion. You're not talking about the other moments of action. You're talking just about action entity, right?
That is true. So the idea is like somehow this translates into avoiding those jerky movements in the first place, because that's the fine level of control you have there. Okay, so we are comparing these three formulations, and all I know so far is one is very hard to specify, and the other two are easy to specify. And so far, I don't know which one will learn fast and which ones will actually achieve the desired behavior. So let's look at that. So I'm going to take soft actor critic, the default hyperparameters, the default network architecture, and then we are going to have a bunch of learning curves. So let's look at the first learning curve. This is with the guiding reward formulation. So the reward has both negative and positive components. So you're going to have a return from the negative to the positive. So each solid line here, that's an average over 30 independent seeds. And the shaded region, that's the confidence interval. So that's a 95% confidence interval. So the learning is fairly robust. Within 10,000 steps, it's like learning just shoots up, it's like it jumps, and then you have something fairly smooth, and then it plateaus. And on the y-axis, all we have is the undiscounted return. So now we see the learning performance on the contract reward formulation. So the y-axis are different in both the plots. So in this case, it's for this reward function. So all you have is positive rewards. So the best you can do is 1,000. The worst you can do is a 0. Oh, yes. Sorry. So you have two variants of the task. You have an easy version and a hard version. If it's easy, the goal is big, the tolerance is big. If it's the hard, the target is very small. So the easy version is orange. The hard version is blue in the first plot. Yeah. Oh, so far I'm just talking about independent learning curves. I'm not going to compare them yet. Okay? So in this case, I'm saying this one also learns. It learns a little slower, but we see some learning curve. And finally, in the minimum time formulation, the plot is not as pretty anymore. It's not as aesthetically pleasing. If you even look at the easy version of the task, for the first 100,000 time steps, there's practically no learning. And in case of the hard version of the task, for the first 200,000 time steps, there's no learning. If I'm a practitioner who's looking at this plot live, I would think this is the failed experiment and just stop there. Right? But all I'm seeing so far is I just have to give it more time, and eventually it converges there. Yes. So because the episode is not done upon timeout in case of the minimum time formulation. So all you have is a reset, and then the episode still continues. You count the steps, and you also bootstrap on the value function. Yeah. So I'm just plotting the undiscounted return here. So even for calculating the return, the episode is not done until you reach the goal. Yeah. So if I just look at these plots so far, I can say guiding reward has fast learning, but it's not easy to specify. In case of the contract reward case, it's like it's not as fast, but it's still kind of fast. So I'm just going to give it a check mark and not say it's at 100%. And in the minimum time case, we don't have fast learning, but we do have ease of specification. So we have some learning curve, but we don't know what the agent actually learned because it just maximized a bunch of rewards. So this was the desired behavior in the first place. We said the arm must reach the target sphere as quickly as possible, and it should stay there. So I'm going to evaluate all these policies using two metrics. So the first metric would be how many steps does it actually take to reach the target? So how quickly does it go to the target? And in the second metric, it's once you reach the target, how long do you stay there? Right? So if I use these two metrics, I know if the agent is actually doing what it's supposed to do. So I'm going to use 500 evaluation episodes for the final model, and each evaluation episode would be 5,000 time steps long. So during training, the time limit was 1,000, but for evaluation, it's 5,000, because I want to see if it can stay there for longer than the training time. So let's just look at the reach or easy plots first. So I'm plotting the number of steps it takes to reach the goal. So first in the reach or easy task, the minimum time formulation, it does best. it reaches as quickly as possible. It's almost thrice as fast as the other formulations. So this one takes about 18 steps. The contact reward requires about 50 steps. Yes.
Now, the clarification is this. Are you taking the asymptotic performance, or are you including the learning ramp up in these blocks?
No, this is a separate evaluation phase. I have the final policy. Yeah. It's, yes. That's it. Yeah, so the previous learning curves you saw, I'm just taking the final checkpoint, and that's it. Yeah. And these are standard errors over 500 different episodes. And I'll check the same with steps on target. So once I reach the target, how long do I actually stay there? So in the first plot, on the left, it's like lower is better, but on the second one, higher is better. So with the minimum time formulations, you stay on target for longer too. So you have a margin of about 500 here. So what you're seeing so far is the minimum time formulation is simply superior to both, even though the learning curve doesn't look as good. And we see something similar with the reach or hard scenario as well, where the guiding reward formulations, like even though it has quick learning, it kind of plateaus to something which is not the best performance. So we have this minimum time formulation, which is still doing better in both the metrics. So if you go back to the evaluation metrics again, with the guiding reward formulation, it's like all I have is fast learning, but it doesn't actually achieve the behavior I wanted. If I use the contact reward formulation, it's kind of the same thing again. It's like I do have fast learning, it's easy for me to specify, but it's somehow not still doesn't achieve the desired behavior. But if you use the minimum time formulation, the learning curves don't look good, but it does get the best behavior. So another question I wanted to ask here was, are the learn policies actually optimal? So I had this question because I first saw this learning curve with the guiding reward formulation. And from about 150,000 time steps till the end, the learning curve just plateaus and it just like stays there around 750. So I'm using a deep reinforcement learning algorithm with no guarantee. So I can't really say anything about convergence or if this is actually optimal. But I can try to get at this empirically. So if I have a different policy, which is better than this policy, I know for sure that this is suboptimal. So, yeah. It's just the best performance you can achieve in the setting. Right, yeah. Right, so based on this, it's the policy with the highest value. So it's the value. Yeah. The return, yeah. The maximum return, yeah. Yes. Yeah. 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 So I'm going to evaluate the policies we get from the other formulation in this task. So I have these policies which I trained in the contact reward formulation and the minimum time formulation. And then I'm going to see if they can actually do better in this guiding reward task. So the policy weights are different, but the task is just the guiding reward task, and you still have the same guiding reward function. So every 10,000 time steps, I'll get the checkpointed model, evaluate it for 10,000 steps, and then have a plot. So if I do it this way, I get this sort of a plot for the contact reward formulation. So it starts out a little slower, but it kind of goes to the same solution, and they have some overlap, so I can't see anything conclusive here. So this were easy, yeah. But if I add the minimum time formulation, it's like for the first 200,000 time steps, it's like it's still suboptimal. So it doesn't do as good, it's still catching up. But after that, it's doing better than the guiding reward policy. So the policy we learned with the guiding reward formulation, it's still not the best compared to a policy I trained on a completely different setting. So I have this minimum time policy, which is being evaluated here, and it's able to do better by a significant margin on top. If I do the same sort of evaluation for the other tasks as well, so let's say instead of evaluating on the guiding reward task, I'll evaluate on the contact reward task. You would notice that the orange and the teal curves swap, which is basically the ordering of the contact reward and the guiding reward switching between the two, but minimum time is still the best. And if I evaluate this on the minimum time task, things are a lot worse. So the other policies are just destroyed here. It's like they don't do anything meaningful. So which raises the question, what did they even learn in the first place? Right? And you see something similar with the hard version of the task as well. So because the task is harder, learning is a bit more delayed, but eventually you see the same sort of a performance. Yes, sorry. So in this case, the minimum time formulation is purple, so that should be the best.
Does this mean that under the evaluation that we're doing class, that the other two are not even reaching the target?
So it still needs to reach the target with the desired velocity. It should be a near zero velocity. So in the other formulations, let's say you just have this arm swinging around, and if you just like randomly pass through the target, you'll still get a reward, but you won't get that in the minimum time formulation. So you should actually stop there. Yeah. So this basically tells us it's maybe hovering around, yeah.
They also have to stay in the target, right?
Yeah, they do have an incentive, but somehow it's not near zero velocity.
Sorry. The problem is that so termination occurs for the minimum time task on what pattern?
It has to reach the goal state, and the velocity should be near zero.
Okay.
Yeah, yeah. So this is kind of what Martha was saying before, where it's like the minimum time formulation should simply just be better, and the others shouldn't be doing so well. So some of the takeaways I had from these experiments so far was the guiding rewards can bias the learn control policy in a potentially suboptimal way. If you have a minimum time formulation, you have a strict hierarchy of policies. You have a clear ordering, because if you just have -1 every time step, you have a clear notion of what is optimal and what is not. So it does make the learning problem a bit easier for the agent. And the sparse reward formulations, they are actually learning better solutions here compared to the guiding reward, the dense reward formulations here. Yeah.
Does it say on the point number 2? I mean, could this not kind of depend on the task? I know this task is fairly straightforward.
Right.
But number 3 is introducing an additional sort of constraint, and that numbers 1 and 2 don't really have any notion of time spent to get to the reward, or it's time to get to the termination state. Well, number 3 does. Like, aren't there tasks out there where that would be an issue? So number 3 is introducing an incentive to go fast.
So that's the case, right? So we have this behavior we want, but there's different ways of formulating the same thing. So it's like based on what you desire the most, it's like what's the desired property for the behavior, it's like that's how it should be formulated.
Are they formulating the same thing now? So number 2 is just
Right. So, but if you do look at the literature, right? So all these papers, they're saying this is the behavior they want, and this is the reward function they're using. I'm trying to make the case that it's not actually getting the behavior you want.
okay
In this case, and why do people use guiding rewards then? So, which is basically a question. So one simple thing is, as an experimenter, it's like I want to see early sign of learning. If not, I get discouraged, I give up on the experiment, and then I move on. And another assumption is that this domain-specific knowledge could help the agent, but it's not really helping the agent in this case. But these are more secondary reasons. I think the primary reason is that some of the empirical evidence, it's like they show that guiding rewards, they still work in the long horizon tasks, while the minimum time formulation doesn't. So let's take these two examples. So on the left, you have robot soccer 1v1. This is from DeepMind. And on the other side, we have the peg insertion task, where there's a square peg. You have to figure out where the hole is, and then you're supposed to insert it and then take it out. So in both these cases, I think it doesn't matter what the reward function is. All I'm trying to say is these reward functions, they're really complicated. And if you look at the robot soccer paper, it's like they have a reward function which goes for about a page. So they have a really complicated reward signal over there. And somehow it's just like deeply unsatisfying to me that we should settle for these biased suboptimal solutions which barely work, because I can get a cute demo out of this, but if I do actually want to deploy this, it's not going to work. I need a solution which will be a lot more robust. So now I was thinking about, okay, so I can't use the minimum time formulation over there, but where can I actually use it? Is there any place where I can use it? So looking at these learning curves, it's like one thing we found out was the speed of learning, it's proportional to the frequency of stumbling upon the target. Because if you have a sparse reward task, until you stumble upon the target, you get zero information about the environment. So if you stumble upon the target more frequently, you're going to get something more informative, and you can learn faster. But your learning could be unsuccessful if the initial policy has poor exploration. And when we learn from scratch, we start with the uniform Gaussian policy, which is just horrible at exploration. So we were trying to figure out if I start with this Gaussian random policy, how far can I get? Can I actually solve something interesting? So based on some experiments, we came up with this hypothesis. So if this initial policy, which is just the uniform Gaussian policy, if it can reach the target at least 10 times within 20,000 time steps, I can have reliable learning using soft actor critic. That's all. So this is a heuristic. This has nothing to do, this is not a theoretical statement. So based on experiments, all we saw was if we have this, maybe we can have learning. So I'm going to try to test it on a bunch of different robot tasks. So I'm going to show you this create reacher task. This is a vision-based task where you have a camera attached on top of a Roomba. You have these 2 green stickers, and you want the Roomba to go as close as possible to this target. So you have camera images, you have wheel velocity information, and for the action space, you're going to control the wheel velocities. So you'll send an action every 45 milliseconds. And we want the Roomba to go to one of these stickers as soon as possible, and that's when the episode ends. So initially, I'm just going to show you the performance of the initial policy. So if you look at it, this is just going to jitter around. It won't do anything meaningful, anything purposeful. And this can be really frustrating to watch because it'll get really close to the target, but it'll never quite get there. But if I watch this for long enough, if I watch this for about 20,000 steps, and if I can evaluate that, OK, so I'll have about 10 hits, so that's when I go for learning. Okay. So this is after about 150,000 steps. So in terms of real time, this is 2 hours of learning, which is not too bad. So you can solve a task like this, which is still fairly complex in the vision space, where this Roomba is able to figure out where it is in space. So it has to figure out that if it's facing a wall, because all the walls kind of look the same. So you have to reverse yourself, look around and figure out where the target is first, and then go towards it. So you reach it, reset to a different location, and it just keeps going on and on. And we also show that with the same learning parameters, the same learning setup, we can have this kind of learning on 4 different robots and 4 different tasks. And these are all variants of reaching tasks, where with the UR5, you have this red dot on a white screen that you're supposed to reach. In case of the vector, it has to find the charger. And in case of the Franca arm, it's supposed to figure out where this red beanbag is and just go there. So I'm not showing the videos for the rest because in the interest of time. So I want to finish with this. So when we all took the RL course, this is something we came across in the RL textbook. And Rich even taught us that in the course. It says the reward signal is your way of communicating to the agent what you want achieved and not how you want it achieved. But let's look at all the benchmark tasks we use. If you look at any of the Mujoko benchmark tasks, except Pendulum, all the benchmark tasks are using guiding rewards. So if there's one thing I want people to take away from this task, from this talk, it's like I want you all to question. It's like we have these nice learning curves, but what did we actually learn? That's it. Thank you. Yes.
Did you look at the behavior? Like, did you run the simulation and see what they were actually doing for all 3 different simulations?
Yeah, so when I was looking at the videos, what I saw was, so for the contact reward and the guiding reward, it would kind of oscillate around within that target sphere. So it's like the velocity is not really 0, but it's still within the target. So you can just keep moving the arm around a little bit so that you're still within the target. But because you do that, sometimes you can step out, and then you have to come back in again. Yeah. Right. So So, so with the minimum time formulation, what we saw in practice was initially have a lot of these big jerky movements. But once you start learning to get to the target, because you need a zero velocity, so you're somehow enforcing that your movement needs to be slow, at least when you're close enough to the target. So the final policy is not really, yeah. Yeah, we care about the final situations. Yeah.
So wouldn't you say adding the constraint that the velocity should be close to zero is also sort of telling the agent how to do the task?
So we have this notion that the arm has to stop there. So how do you encode that? So, right, so it's like the agent can still figure it out on its own if it's like a task that it has to, yeah.
Sorry, the action is square in the first reward, so it is not for guiding the agent. It is for limiting the energy consumption. Isn't it like that? So we really wanted to have it in our reward. So this was my understanding from several Mujuku environments that have this action. For example, you had a slide and you said that every Mujuku environment except for I think Pendulum, they all like have a guide the agent, but if you are you considering the action square minus action square as a guide? Or
so in this case, I just wanted to point out there's like an existing reward, and I wanted to compare against this. So one of the reasons, like you said, is to make sure that you don't spend too much energy. But it also, there's also other papers where they cite this as a way to make sure that you dampen the movements. You want to make sure that you don't make big actions.
Okay, so no, I wonder if this is a favorable thing to consider, not for
right.
guiding, but for limiting the energy consumption, then if you consider it also in the two other reward formulations, I don't know how, so it's clear for the second formulation, and in the third formulation you could also subtract the action square from 1 or something like that. So in that case, I wonder how would the performance of different algorithms compare in terms of convergence time.
So I think, and my intuition says, the less bias you have, the better it should be. The final solution. I'm not talking about intermediate performance. So if you just add the same action penalty to all the three formulations, I think the minimum time would still do the best.
It is not at all clear, because so you look at the second line of the reward in the first reward function. So the distance term favors achieving the goal sooner, but the action square does exactly the opposite. Okay, so it is not clear if you consider the action square, for example, in the second formulation to be fair, for a fair comparison, then which one results in a faster reaching the target.
That's something I think I'll have to test out and figure out, but I don't have an answer for that now.
Okay, we are.
Sorry, the time is up. If you have questions, we can after talk to Gautham after talk. Thank you.
Okay. Yes. Oh yeah.